Okay, good morning, class. Okay, today we look at the application of matrix. Yeah, application of matrix, eigenvalues and eigenvectors. Okay, so this is the lesson outcome for this week. So at the end of this week, you should be able to compute all the eigenvalues and their corresponding eigenvectors by using polynomial method. And the second method, power method, it just provides the dominant eigenvalue and its corresponding eigenvector. Okay, so for an n by n matrix, okay, there are n eigenvalues. Okay, for example, 3 by 3 matrix, we have 3 eigenvalues. So each of these 3 eigenvalues, they have their own corresponding eigenvectors. Okay. So one eigenvalue with one eigenvector. So from that 3 eigenvalues, and these are the all eigenvalues. For 3 by 3 matrix, we have 3 eigenvalues and 3 eigenvectors if you use polynomial method. But if you use power method, we are just able to find the dominant eigenvalue. This means among the 3 eigenvalues, we just obtain the dominant eigenvalue. Okay, there's only one. Okay, one set. Okay, and the difference between these two are, okay, polynomial method is an analytical method. Okay, this one we need some derivation, okay, from solving the linear equations, linear system. For the power method, this is under numerical. Okay, this is numerical method. This means it involves a lot of calculations. Okay, today we will look at polynomial method. Okay, why we need eigenvalues and eigenvectors? Okay, we need this to study differential equations and also continuous dynamical systems. Okay, because they provide some critical information in engineering design. Okay. And normally, dominant eigenvalues are the primary interests in many of the real-life applications. Okay, they want only the dominant eigenvalue. Because in the real-life problem, normally the size of the matrix is very huge. Okay, very huge. That is impossible for us to find all the eigenvalues, okay, from that kind of matrix. Okay, normally, the dominant eigenvalue, it provides the critical information. Okay, so we just find for the dominant one by using power method. Okay. Okay, next one we look at what is an eigenvector and eigenvalue. An eigenvector of an n by n matrix is a non-zero vector V. Okay, we denote it as V. Non-zero vector, it means these are non-zero vector. Okay, non-zero vector. This is called zero vector. So your eigenvector must be non-zero vector, something like this. Okay, we can't accept all zero. Okay, we don't want this kind of eigenvector. Okay, and the matrix, okay, the relation between matrix, eigenvector, this one eigenvector, and also the eigenvalue, okay, is given by this AB equals to lambda V. Okay, this lambda is called an eigenvalue. Okay, if there is a non-trivial solution V. Okay, why we call this as non-trivial solutions? Because this is the problem. Okay, this problem we can write this problem as a linear system. Okay, write this as a linear system, and we solve the linear system, and we get a solution. And that solution V, we want the solution V, and that V must be a non-trivial solution. Okay, so there are 2 types of solution. One is trivial, another one is non-trivial. Okay, trivial solution means the solution contains all zero. Okay, contains all zero. This is a zero vector, right? V is a zero vector. So when V is the solution, this solution is called as trivial solution. What we want is a non-trivial solution. We want the solution to be something like this. Okay, at least one of the entry is non-zero. Okay, the solution of the V must be something like this. Okay, it must be a non-trivial solution. Okay, so the vector must be something like this. Okay, now this is an example that shows the matrix, how the matrix, the eigenvector and eigenvalue, okay, satisfying this relation. Okay, so A times V, okay, A times V. So this one, matrix A and vector V. So when we multiply these two, we use raw column, we get this. And then raw column, we get this. I hope you still remember how to multiply the matrix and also the vector. Okay, then the next one, if you factorize -4, you get this. Okay, after you factorize. Okay, and this one, this is same as this. Okay, this is the eigenvector. So this is the eigenvalue. Okay, it shows how these three are connected through this relation. Okay, so this V is an eigenvector of A corresponding to the eigenvalue of lambda. Okay, we use corresponding because lambda 1 has eigenvector B1, lambda 2 has an eigenvector B2, okay, lambda 3 has an eigenvector of B3. They comes in a pair, okay, they comes in a pair. So this is the eigenvector of this eigenvalue. When you have more than 2, this means 3 by 3, 4 by 4, you have lambda 1, lambda 2, lambda 3, lambda 4. Okay, and they have their own eigenvector. Okay, so we call that as a corresponding eigenvector or corresponding eigenvalue. Okay, so before that, you have to know, okay, how to solve a linear system. Okay, in the week two, you have learned how to solve the linear system that provides a unique solution. Okay, the one you learn, Gauss elimination, Gauss Seidel, LU decomposition, they are all all these three methods, it gives unique solution. That means you have only one solution. Your x, y, z equals to one vector. Okay, three different figures, just one solution. That is unique solution. Okay, why we get unique solution? Because the number of leadings or number of pivots is the same as the number of variables. Okay, this x, y, z or x1, x2, x3, these are called variables. So there are three variables and three pivots. Okay, when the number is the same, okay, then we say that this linear system, it gives a unique solution. So these are the linear system that you have encountered in week 2. Okay, week 2. Okay, this one, it must be in echelon form. Okay, we reduce into echelon form and then only we count how many pivots, how many variables. Okay, then we know whether it provides you no solution or unique solution or many, okay, infinite many solutions. Okay, but remember, when the number of pivot is the same as the number of variables, it gives only one solution, unique solution. Okay, now we look at no solution. Okay, under what situation a linear system gives no solution? Okay, if you look at this one after we raw reduce, we get this. This is in REF, okay, raw echelon form. If you look at the last row, okay, let's say this is x1, x2, x3. When you form the equation from the last row, you have 0x1 plus 0x2 plus 0x3, which is 0 on the left. But you have a non-zero on the right. That is impossible, right? 0 equals to 5 is impossible because 0 is not equals to 5. So this linear system, it gives no solution because this linear system is inconsistent. Inconsistent. Okay. I repeat, in a raw echelon form, when you get all zero on the left and non-zero on the right, that means this linear system, it gives no solution because it is an inconsistent linear system. Okay, and there's one more type, which is infinitely many solutions. Okay, many solutions, infinite. Okay, infinite. So the solution number of solutions is infinite, infinity. Okay, infinity number of solutions. Okay, so this one is the number of leadings or pivots less than number of variables. Okay, for example, this one. There are 4 variables. Okay, there are 4 variables, but we have only 2 pivots. Okay, remember this. Each of the row, it has only 1 pivot. Second row, you have only 1 pivot. Okay, so that means this linear system, it gives infinitely many solutions. Okay, and we say that no leading for y and z. Okay, w has a leading, okay, or pivot. Okay, here I use leading because this is in the raw reduced echelon form, RREF. So that is leading. But normally we just raw reduce until raw echelon form. We don't change all this pivot into one. So that's why I call that as pivot. I use the word pivot. Okay, so the W has a pivot, X has a pivot, Y and Z has no pivot. Right? Y has no pivot, Z has no pivot. These two are pivots. Or no leading or no pivots for Y and Z. And same goes to this one. Okay, you have 3 variables, but you have only 2 pivots. X has a pivot, Z has a pivot, but Y has no pivot. Okay, no leading, no pivot. So when the variable has no pivot, we say that that variable is free. That variable is free. Y is free, Z is free. Okay, here Y is free. What it means free? It's free to be any values. Free to be any values. Okay, it can be any values. Okay, there's a note here. The staircase is allowed to move horizontally. Okay, that means to the right. This one horizontally to the right across more than 1 and 3. Okay, that's when you see this is 1 and 3. It crossed 1 and 3, and for this part, it crossed 1, 2, 3. Okay, it can cross the horizontal line. It can cross more than 1 and 3, but the one vertical line, it can only cross 1 and 3. Then it needs to go to the right. Yeah. Okay. And moves down across only 1 and 3. Okay. You see, there's only 1 and 3 allowed. This one, 1 and 3 allowed. Then it needs to turn right. But the horizontal line, it can cross more than 1 and 3. And the entries underneath the staircase is all zeros. Okay, all zeros. Okay, then now we look at one example, how to get the solution for the case of infinitely many solutions. Okay, now given a linear system, okay, this is already in raw reduced form. Okay, so we don't have to raw reduce anymore. Okay, so when you sketch the staircase, okay, this is the pivot. Okay, there's a non-zero, so it goes down and then cross. Okay, here 0, so it cross 1 more. Okay, non-zero, goes down and turn right. So this is the staircase. And W has a pivot, X has a pivot, Z has a pivot, Y is free. Y is free. So since there's no leading in the column of Y, okay, or we say that Y is free, hence we would let Y be C. C is a constant. C is the real number. Okay, C is a real number. Okay, C can be any values. Okay, then we perform backward substitution. So from the last row, we have 1 Z equals to 1. Okay, Z equals to 1. Then from the second row, we have X equals to 2. Okay, and from the first row, we have W plus X plus 2Y equals to 1. This one. Then we substitute the X, y, and z into xy here. If we need only xy, so we substitute x by 2, y by c, then we want w. Okay, so your w will be in terms of c. Okay, then you put the w, x, y, z into the vector form. Okay, display your answer in a vector form. Since your answer contains value only, and also another one contains c. Okay, you see values only, there is a c here. So we break this, we separate this solution into two groups. One is just the value without c, another one with c. Okay, so this is -1. Okay, for the coefficient of c, you have -2. Okay, this one constant, the value only, so 2, there is no c, so 0. Okay, 0 c, that means 0. Okay, c, so 0 plus 1 times c. Okay, and 1, there's no c, so no c, 0, and here this is 1. Okay, and finally you put a notation c is the real number. Okay, this is a real number system. C is a real number. Okay, any values. Okay, this is how we get the solution for the case of infinitely many solutions. Okay, because from here we have already know this will give infinitely many solutions. There are 4 variables, but there are only 3 pivots. Okay, so infinitely many solutions. Okay, any questions? Okay. Okay. Okay, we try this. Try this. Okay, you sketch the staircase. Okay, see, this one is non-zero, so this is a pivot. Okay, when you see a non-zero, it goes down and then cross. Okay, non-zero, so it goes down and cross all the way, okay, to the last. So this one, let's say I use x1, x2, x3, x4. Let's say I give the name x1 up to x4. So this is the pivot, this is the pivot, and this one, this is the pivot. So which one is free? X4. X4 is free. So when X4 is free, we let X4 be C. And this C you need to denote C is in real number. Okay, C is real number. It can be positive, can be negative, can be fraction, can be integer. Okay. Then perform backward substitution. Okay, backward substitution from the equation from the last row, and then you substitute X4, obtain X3 in terms of C. These are, okay, when I write, I put a double line. Right. This denotes the real number system, just like what you see from the slide. This one R. Okay. When we type this R is, can you see the R? The R is in this form. Real number system. Okay, in the system of number, we have real number and complex number. Okay, real number and complex number in the number system. And in the real number, we have integer, non-integer. Integer we use set. Okay, and then we have the rational and non-rational number. Okay, rational we use what? I can't remember. Integer we use set. Okay. Okay, that is the number system. Okay, R is just the number which is not complex. Real number. Complex that still be done the imaginary part. Okay, the one with I. Okay, I is for C for complex number. Okay, R for real number. Okay. So here your x3, okay, x3 plus x4 equals to 1. So x3 is 1 minus x4. Okay, 1 minus x4. Then from the second row, you have x2 plus x3. x3 equals to 2. So we want x2. x2 is 2 minus x3. 2 minus x3, your x3 is 1 minus c. Okay, so you get, what do you get? 1 plus c. Okay, and from the first row, we have x1 plus 2x2 plus x3 plus 4x4 plus 3. Okay, so x1 is 3 minus 2 x2. x2. Okay, minus x3. And then minus 4 xc. That's x4. So when you simplify, you get 3 minus 2 minus 2c minus 1 plus c minus 4c. 3 minus 2, 1. 1 minus 1, 0. So negative 6c plus c. So negative 5c. Okay, then put your answer x1, x2, x3, x4 into a vector form. x1 is negative 5c. x2 is 1 plus c. x3 is 1 minus c. And x4 is c. So this one you need to practice into 2. Cari apakah itu X1, X2, X3? Dia nak carikan jawapan untuk pilih sistem yang. Okay, this is actually similar with one you have learned in Big 2. But the one in Big 2, we do not have C. Your solution does not contain C because it has unique solution. The solution is unique. Okay, but for this case, the number of variables is more than the number of pivots. That's why your answer contains C because it will provide you the infinitely many solutions. Okay, now you look at this one. Why we say that C is any numbers? Why we say that this is infinitely many solutions? C can be any values. Let's say C is 1. When C is 1, you have -5, 2, 0, 1. When C is 2, you have another set of vector. When C is -1, when C is 0.1, 0.5, a lot of choices, infinitely choices for the C, right? Because C is a real number. That's why we say that this solution has infinitely many solutions. Because it depends on the C. C can be any values as long as it is a real number. Okay, so now this one, we want to separate this into 2. So -5c, 0, -5. Because this contains C, right? The coefficient of C is -5. Okay, this one, 1 plus C. So 1 plus, the coefficient is 1. Coefficient of C is 1. And this one, coefficient of C is -1. And this one, C, 0, 1. Okay, any questions? Okay, this one I repeat once again. Why x4 is the pivot? Okay, look at here. When you sketch this, okay, actually you know that this is the pivot. Okay, this is the pivot. This is also the pivot because the pivot must stay on the line, the horizontal line. So here, there is only one value stay on this. This, they are not staying on the line. So this row, this is the pivot. Second row, only this stay on the horizontal line. So this is the pivot. Okay, here, the third line, these two stay on the horizontal line. Pivot must be non-zero and free. So the pivot can be this one or this one. But remember this, one row has only one pivot. So this row, if you say that this is the pivot, that means this is not the pivot. If you want to say that this is the pivot, then this is not the pivot. Okay, so now normally we choose the first one. We choose the first one to be the pivot. So last row, this is the pivot. X1 has a pivot, X2 has a pivot, X3 has a pivot, X4 no pivot. That's why X4 equals to a constant. Okay, X4 is free. Okay, any more questions for question number 1? So number 1. If no, proceed to number 2. Okay, number 2. Can I run this off? Okay, number 2. So for question number 2, sketch the staircase. Okay, sketch the staircase. So see, this one, this is non-zero. Okay, we have a horizontal line here. And this is all 0, so we continue. Okay, up to here, there's a non-zero. Okay, so it goes down. Okay, after it goes down for 1 unit, across 1 unit vertically, then you need to turn right. Okay, and up to here, this is 0, so we continue. Okay, let's say this is x1, x2, x3, x4. So which one is the pivot? 1, right? This one. And then 3. X3 has a pivot. Okay, because one row has only one pivot. One row has only one pivot. Pivot must be non-zero. All 0, that means no pivot for the last row. Okay, we have 4 variables. We have only 2 pivots. That means infinitely many solutions. And which one is free? X2 is free. X4 also free. So we let X2 be C1, X4 be C2. They are both constant, but they are not the same constant. That's why we use different labels, C1, C2. If there is only one variable is free, we just use C. If more than one, we use C1, C2, or even C1, C2, C3. Okay? Because there are constants, but different constants. So this one, C1, C2 are in real number. Okay, in real number system. Then backward substitution. Start from the second row. Form the equation from the second row. Substitute x4. Then solve for x3. Not really one. This one, it can be any values as long as non-zero. Because when you row reduce the matrix, we just reduce up to REF, not RREF. Okay, in REF, all pivots must be 1. Because we saw at REF. So your pivot and is non-zero values. Okay, from the second row, we have x3 plus 2x4 equals to 5. Okay, so just substitute the x4. Your x3 is 5 minus 2x4. Okay, and from the first row, we have x1 plus 2x2 plus 3x3 plus x4 equals to 4. Okay, we want x1. So x1 is 4 minus 2x2 minus 3x3, x3. Then minus x4. Okay, then I continue here. Your x1 will be 4 minus 2c1 minus 15 plus 6c2 minus c2. Okay, simplify. 4 minus 15, negative 11. Okay. One, two, three, 1, 4. Okay. Then minus 2C1 minus plus 5C2. Okay. So your x1, x2, x3, x4 will display them in the form of a factor. X1 is negative 11 minus 2C1 plus 5C2. X2 is C1. X3, 5 minus C2 minus 2C2. X4, C2. Okay, then you break this into the values only, the one with C1, the one with C2. And then you denote here C1, C2 in real. Okay. So negative 11. The one with C1, the coefficient is negative 2. The coefficient for C2 is 5. Okay. And for X2, C1. Okay, C1 here. 0, 0. 5 minus 2 for C2. Okay, 0 for C1. And the last one, 0, 0, 1. Okay. Anyone? Yes, 1 or 2. Okay. Any more questions for number 2? You need to know this for this polynomial method. Okay, when you find for the eigenvector, you have to know this. Okay. Okay, now we continue with the polynomial method. Okay, so from this relation, okay, we know that lambda is the eigenvalue, v is the eigenvector. So from here, we want to solve this equation to obtain the lambda and also v. Okay, so since there are two v's here, there are the same v. So we want to move this term to the left and factorize the v. Okay, we want to solve for the v. Okay, but this one, we can't move directly to the left. Okay, because A is a matrix, lambda is a constant. If you move this to the left and you factorize the v, that means you have A minus lambda, right? A minus lambda. If you move this one to the left and we factorize the v, that means you have A minus lambda in the bracket times v. But what is A minus lambda? A is a matrix, V is a A is a matrix, lambda is a constant. We can never minus a constant using a matrix, right? How matrix minus a constant? Impossible. It must be matrix minus matrix. So we can't move this directly. We have to multiply an identity matrix to this part. Okay. When you multiply identity matrix, the output is still the same. Lambda V is still same with the lambda IB. Okay. But when you move this to the left and you factorize the V, now this is a matrix. This is also a matrix. Lambda multiply into the matrix of identity. So this is a matrix. So now we can this is valid now because matrix minus a matrix. Okay, so this is a linear system. This is similar to the last time we used AX equals to B. You still remember the A matrix A, and then X is the X1, X2, X3, X in bold equals to B in bold. B is the right hand side value, B1, B2, B3. Okay, that is a linear system. AX equals to B. So this is your AX equals to B. Okay, this is not zero. This is a zero vector. Okay, this zero is in bold. Okay, zero in bold. This is a zero vector. Because this one, AV, A times V is a vector. Lambda IV is also a vector. Vector minus vector, it must be a vector. It's just that this is a zero vector. Okay, zero vector. Okay, so now we obtain a linear system. This is similar to the AX equals to B. Okay, to solve this, we want to solve for the V. Okay, we want to solve for the V. But remember, V cannot be zero vector. We don't want V to be zero vector. We want to find the eigenvalue in such a way V is not zero vector. Okay. Hence, to find the eigenvalues, we need to solve the characteristic polynomial. Okay, this is the characteristic polynomial. This comes from here. Okay, and this determinant must be equals to zero. Okay, determinant must be equals to zero. Okay, I relate a little bit of this. Why determinant equals to zero? B. I can't use this. I take a 3 by 3 matrix. This one. This one, it gives infinitely many solutions. Okay, that means if this is your V, okay, your V is X, Y, Z, let's say. This is what we want. Okay, this is what we want. Because we want our V to have the solution, not the no solution. Okay. And you can't get something like this. If you have something like this, you have only unique solution. Okay? You have only unique solution. For this kind of case, if you find for the determinant, what is the determinant? What is the determinant? Zero. It must be zero. Okay. So that's why here, the determinant of this, it must be zero. Okay. We want to find the V, which is non-zero. Okay. We want the V to be non-zero. Okay. For this kind of case, what do you think? What is your V? If you solve for this, what is your V? Let's say your V is X, Y, Z. Try to think. If let's say your V is X, Y, Z, based on this, what is your V? Backward substitution. When you apply backward substitution, what is your Z? Zero. What is your Y? What is your X? Zero. All zeros, right? That means your V will be zero. We don't want something like this. Our V must be non-zero, right? That's why we want something like this. The solution is something like this, right? This is not zero. This is what we want. Okay, this is what we want. So that's why the determinant for this part, it must be zero. Okay? It must be zero. Okay, this is why we need to find for the determinant of this part, and we let it equals to 0. Okay, that's the idea behind. Okay, that's the idea behind. Because we want something like this. We don't want V to be all zeros. Okay, so now we look at two examples. Okay, we look at the one with 2 by 2 matrix first. We want to determine the eigenvalues by using polynomial method and find for their corresponding eigenvectors. Okay, we look at the first one, matrix A. Okay, matrix A, this is your matrix A. Okay, remember to get the eigenvalue, okay, to get the eigenvalues, you need to find for this. Okay, you need to find for this. What is this? This is the determinant. Okay, determinant of the matrix A minus lambda I. Okay, this is matrix A minus lambda I. Okay, so A minus lambda I, you get this. So in simple words, A minus lambda I means you just need to minus lambda for the diagonal entries. Only diagonal entries minus lambda. So 2 minus lambda, -6 minus lambda, and the rest remain the same. Okay, once you get this matrix, we find for the determinant. Okay, we find for the determinant and we let this equals to 0. Okay, then to get the determinant of this 2 by 2 matrix, we use AD minus BC. Okay, so AD here minus BC. So this one equals to 0. Okay, it needs to be 0. So this one, you simplify, you get this. Okay, expand. Okay, expand, simplify, you get this. And from here, you can use your calculator to do the factorization to get for the values of lambda. Okay, it doesn't matter whether this is lambda 1 or lambda 2 or lambda 1, lambda 2, it doesn't matter. Okay, for polynomial method, it doesn't matter which one is lambda 1. Okay, as long as 2 by 2 matrix, you get lambda 1, lambda 2. Okay, and it is possible for lambda 1 and lambda 2 to be the same. It's possible. Okay, but at the end, you will get lambda 1 and lambda 2. No matter they are different or the same. Okay, you must have lambda 1 and lambda 2. Because this is a 2 by 2 matrix. Okay, we skip to the question number 2. Okay, question number 2, we just look at the eigenvalue part first. Okay, this is the matrix. So to get the eigenvalue, what we do, we use the main diagonal entries all minus lambda. So this is 1 minus lambda, negative minus lambda, 1 minus lambda, and then the rest remain the same. You get this. See, the main diagonal all minus lambda. And the rest of the entries that remain the same. And now we want to find for the determinant and we let it be 0. Okay, we let it be 0. It's not that you find and then at the end you get 0. We let this to be 0. Okay, so from here you can apply the shortcut. 1, 2, 3, you get this. 1, 2, 3, you get this. 1, 2, 3. The 1, 2, 3, that's when you multiply the 3 entries. You get this. Then minus the other direction. 1, 2, 3. Okay, you get this. 1, 2, 3. You get this. And then 1, 2, 3. Okay, simplify, expand, expand, simplify. You get this one. Factorize and get your lambda. Obtain your lambda. This is how we find for the eigenvalues. Okay, any questions? Just use the given matrix, main diagonal entry, all minus lambda. Then find for the determinant, let it equals to 0, and then we solve for the lambda. That is your eigenvalues. Okay, next we look at how to get the corresponding eigenvector. Okay, we're back to the question number 1. After you get the eigenvalues, Okay, the first eigenvalue is 3. Lambda 1 is 3. Okay, now we want to solve for this one. Okay, we want to solve this for V. Okay, solve for V. So this lambda is 3. Okay, 3. That means we substitute this lambda by 3. Okay, this is 3, so we substitute this lambda by 3. So you get 2 minus 3. This is negative 6 minus 3. Then you get this. And this is a linear system. Okay, this is a linear system. The right-hand side vector is 0 vector. So that's why you get all zeros on the right. Then simplify. Okay, simplify. You get this augmented matrix. Then you need to row reduce the matrix to get REF. Okay, once you get REF, okay, then back to this. This one, how to get the solution? This is the way. Okay, so you sketch the staircase. This is x1, this is x2. x1 has a pivot, x2 is 3. That's why x2 equals to a constant. The constant is a real number. Then you form the equation from the first row. Substitute x2, solve for x1, put your x1 and x2 in a vector form, this one, and then factorize the c. Okay, this is your eigenvector. This is your eigenvector. C is a real number. C can be any values. If your C is 1, your V1 is 3, 1. If your C is 2, your V1 is 6, 2. If your C is 1 over 3, you get 1 and 0.3333. C can be anything. So we want to standardize. We want to standardize the eigenvector. So we normalize it. We normalize the eigenvector so that everyone get the same eigenvector. Okay, otherwise, 60 students, 60 different solutions. Okay, so normalize the eigenvector. That means we let, okay, normally we just let C equals to 1. You can let C to be any values, but after normalize the vector, you should get the vector with the entries, okay, the entries that has the largest magnitude of 1. Okay, this one you see, this is more than 1. This is more than 1. After normalization, we expect to get the entries with the largest magnitude of 1. Okay, so this is 1, this is less than 1. This is what we want. Okay, so how to normalize? Okay, if you follow the standard way, you just let C be 1. Okay, you let C be 1, then you have 3, 1. Okay, 3, 1. Then we select the entries with the largest magnitude, which is 3. And then we divide all the entries by 3. Okay, we divide all the entries by 3. So that's why we get this. Okay, so this is your V1. Okay, this is your V1. Any questions? Okay, next we look at the second lambda. We have the second lambda. So you repeat the same way. You substitute lambda into this one, into here. Okay, second lambda is negative 7. So 2 minus negative 7. Negative 6 minus negative 7. Okay, 3 here. Okay, so this is the matrix on the left. This is an augmented matrix. Huh? Remember, you have to form an augmented matrix where the right-hand side is all 0. Okay, all zeros. Simplify, you get this augmented matrix. Row reduce, you get this. Sketch the staircase. X1 has a pivot, X2 is 3. Okay, X2 is C. For the equation, substitute your X2, solve for your X1. And then display your X1, X2 in the vector form, factorize the C. Okay, and you see this is what we want, right? The largest magnitude is 1. the magnitude is 0.3333. This one magnitude is 1. So this is actually what we want. So we just let C be 1, then we get our V2. Just let C be 1, then this is your V2. Okay, now we look at the question, the second question just now. Okay, we obtain this one, lambda 1 is 1. So we substitute this lambda by 1, 1, 1 here. Then we form this on the left. And on the right, it will always be zeros. Okay, so here we row reduce. But before row reduce, you have to change. Okay, you have to swap these two rows. Okay, either first row with second row or first row with third row. Okay, because this should be a non-zero pivot. Okay, this should be a non-zero pivot. So after you swap, you row reduce. Okay, sketch the staircase. Your staircase is this. Okay, so this is the pivot. This is the pivot. X3 is free. So X3 is a constant. Then you apply the backward substitution. Okay, then you get this equation, substitute your X3, solve for X2. And finally, from the first row, you get this equation, substitute X2, you get X1. And put your X1, X2, X3 into a vector, factorize the C. Then this one, actually, this is what we want. So we just let C be 1. Then you get your V1. Okay, the same process with the 2 by 2 matrix just now, right? Okay, so what is the difference now? Here, your lambda 2 and lambda 3 are the same, which is -2. So now we substitute this lambda back into here. Okay, this value, we put it back here. Then you get this. On the right, all zeros. So now you row reduce and your staircase will be a horizontal line. So X1 has a pivot, X2, X3 are free. That's why X2 is C1, X3 is C2. Then from the first row, you come up with the equation, substitute X2 and X3, solve for X1, put your X1, X2, X3 into a vector. Okay, now you have C1, C2. That's why you need to break this into 2. One for C1, another one for C2. Okay, so this one, okay, this one, your V now is this. This is actually what we want. This is also what we want because the largest magnitude is 1. So we just let C1 and C2 by be 1. We let them be 1. So if C1 is 1, this is your V2. When C2 is 1, this is your V3. That means when you have the same eigenvalues, from that eigenvalue, you will get 2 eigenvectors by having C1, C2. Okay, you can assume that this one we break it into 2. Okay, one for the first, another one for the second eigenvectors. Okay, so for the eigenvalues of this is their eigenvectors. Okay, and of course, you can say that this is the V2, this is the V3, doesn't matter. Okay, because their eigenvalue is the same. Okay, any questions? This one you need to go through some exercise, okay, to understand the flow. Okay, now we try this. We try this exercise number 1. Okay, to get the eigenvalues, okay, this is what you need to do. Okay, form the determinant. Okay, straight away form the determinant. Use the diagonal entries minus lambda. Okay, so 1 minus lambda, 2 minus lambda, you let it be 0. Okay, and then we solve for the determinant. Okay, we let it be 0. Sorry. We find the determinant, we let it be 0, then solve for the lambda. Okay, AD minus BC. So I know AD minus BC. Expand, simplify, factorize. Okay, expand 1 times 2. And then minus lambda minus 2 lambda plus lambda squared minus 30 equals to 0. Then lambda squared minus 3 lambda minus 28. Factorize. Okay, so lambda plus 4 lambda minus 7 lambda plus 4. Okay, so your lambda 1 is 7, lambda 2 is negative 4. Okay, next. Your lambda 1 is 7. Okay, do like this. Okay. Lambda 1 is 7. So you form the augmented matrix. You form the augmented matrix. How to form? What is your A? What is your matrix here? You substitute 7 into here. Substitute 7 into here. So 1 minus 7, -6. This is 6. This is 5. 2 minus 7, -5. 0, 0. Form the augmented matrix directly. Then row reduce. Okay, row reduce. After row reduce, sketch the staircase. Identify which variable is free. That n equals to c. And find for the x1, x2. Okay, so what is the operation? 5/6 R1 plus R2. Okay, so you get a negative 6, 6, 0, 0, 0, 0, right? Okay, so this is the pivot. Okay, let's say x1, x2, but so x2 is free. So we let x2 be C. C is a real number. So from the first row, we have negative 6x1 plus 6x2 equals to 0. Okay, 1x1. So 6x1 is 6x1 equals to 6x2. That's why x1 is C. Okay, then your V1. Okay, V1 is x1, x2. Okay, this is your V1. Okay, so this is actually what we want. The largest magnitude is 1. So we just let C be 1. Then we get our V1. Okay, continue from here. So by taking C equals to 1, so your V1 is 1, 1. Okay, your V1 is 1, 1. Okay, then repeat the process by using lambda 2. Okay, lambda 2 is -4, right? -4, okay. So just now you have 1 minus lambda. So 1 minus -4. You get a 5. And then 6. Then 5. 2 minus -4. Okay, that's been 2 plus 4. Get a 6. Substitute into the A minus lambda I. You just now you have A minus lambda I as 1 minus lambda 6, 5, 2 minus lambda I. This is your A minus lambda I. So you substitute your lambda 2 into this and this, you get this.
Power
Right hand side? Yes, right hand side is always 0 because we are solving for this. A minus lambda I B equals to 0 vector. Okay, we are solving for this. That's why the right hand side for the augmented matrix is always 0. Okay, so this one you already use. You get a negative R1 plus R2, right? So 5, 6, 0, 0, 0, 0. Okay. Staircase, pivot, x1, x2, x2 is 3. Okay, x2 is 3. So we let x2 be c. C is a real number. And we have 5x1 plus 6x2 equals to 0. Okay, so 5x1 is -6c. Okay, then I continue here. So your x1 is -6 over 5c. Okay, x1. Yes. So your V2 is -6 over 5c and c. Factorize the c, you get -6 over 5 and 1. Okay, this one we have to normalize it because the 6 over 5, this and 3, the magnitude is more than 1. Okay, the magnitude, the largest magnitude is more than 1. So now by taking c equals to 1, your V2 will be -6 over 5 and 1, right? When c is 1, we have this. But we want to normalize this. So we divide all the entries by the entry with the largest magnitude. -6 over 5. We want to normalize this by dividing all the entries by the entries with the largest magnitude. Okay, so we get 1 and -5/6, right? -5/6. -5/6 is -0.833. Use 4 decimal places. Okay, very simple. If you manage to remember the flow, you have to know what you need to solve. Okay, then you know what are the steps. Any questions? When? Okay, here up to here, we will check. Is it all the entries as is it the entries with the largest magnitude is 1? This 6/5 is more than 1. When this is more than 1, we have to divide. We have to do the division. So this is the entry with the largest magnitude. So we choose this. So all of this you need to divide by this value. Okay, so that your eigenvector, the largest magnitude is 1. Okay, but of course, let's see one first. Let's see one. Then we choose the largest magnitude, the one with largest magnitude, we divide all the terms by that value. Okay, after you divide this one cancel with this, automatically you get 1. And the rest of them, it must be less than 1. Because this is the largest magnitude. Okay, this has the largest magnitude. Okay, that's why you have an extra steps. Just now you have 1, 1, right? The first V1 is 1, 1. We don't have to do this because the largest magnitude is 1. That is what we want. Okay, that is what we want. But this one, this is already more than 1. Okay, sorry, this is already more than 1. That's why we need to divide. Okay, whenever you see the entry more than 1, that means you did this step. The largest magnitude, the entry with the largest magnitude must be as long as out of all the entries, the largest magnitude. Before the negative, that's when you just divide the 6/5. Oh, okay. This one is largest one. Yeah, which is
Any more questions?
Okay.
This one actually you can say eigenvalue and eigenvectors is correct. Remember the relation A lambda equals to AB, sorry. AB equals to lambda B, right? Plus, from this relation, actually, you can know whether your answer is correct or not. Because your eigenvalue and eigenvector, and also the matrix, it must satisfy this relation. When your A, this is your A, B, this is your B, lambda. This is your lambda. Okay. When you can do the checking on your own. Just like the linear system. Okay, just like the linear system, when you substitute the x1, x2, x3 back into the linear equations, you should get the same values, right? Just Okay, can we proceed to question number 2? Okay. Find for the eigenvalues. Let all vector entries minus lambda form the determinant that is value 0. Form the determinant 3 minus lambda 6 negative 8 0 0 minus lambda 6 0 0 2 minus lambda. Okay. Get the determinant of this 3 by 3 matrix.
Oh, gitu.
This question, you can get the eigenvalue in just a few seconds. Look at here. How do you get the determinant for this matrix? You use vector expansion. You use shortcut. What else? Look at this. What is this matrix? This is a triangular matrix, right? Triangular matrix, when you get the determinant, we just need to multiply this one with this one with this one, right? 3 minus lambda, 0 minus lambda is negative lambda, 2 minus lambda equals to 0. So lambda 1 is 3, lambda 2, I use this one, 2, lambda 3 is, I use this, 0. I want to follow the sequence of the slide so that you won't get confused when you compare your answer. Okay, 3, 2, 0. This one, you don't have to expand. You expand, then you simplify, then you factorize to get this back again. Right? So just from here, get your eigenvalues, proceed to your eigenvalues. This one. Okay. Say lambda 1 is 3. Okay, lambda 1 is 3. So substitute the lambda by 3. Okay, this one, 3, 3, 3. Form the augmented matrix. Then reduce. So 3 minus 3, 0. 6, negative 8, 0, negative 3, 6, 0, 0, negative 1. Okay, 2 minus 3, negative 1, and then all 0. Okay, row reduce. Okay, the first row, suppose this is the pivot position, but all the entries underneath are all zeros. Okay, so we can't swap any rows. So what you can do, you just ignore the first column, take this as the first pivot, use this to row reduce this into 0. Okay, so use this to row reduce this one into 0. So your operation is 3 over 6 is 1 over 2, right? R1 plus R2. 0, 0, negative 4 plus 6. Negative 4 plus 6, 2. Then 0, 0, negative 1, 0. Okay, so when you sketch for the staircase, okay, it goes down, then you need to turn right. So now use this to change this into 0. 1 over 2 R2 plus R3. Okay. One row has only one pivot. Okay, one row has only one pivot. So which one is free? X1 is free. X2 has a pivot here. X3 has a pivot here. X1 is free. Okay, then backward substitution. X3 equals to 0. Then first row is 6x2 minus 8x3 equals to 0. Okay, 6x2 equals to 8x3. X3 is 0. So your x2 is also 0. So your V1. V1, x1 is 3. X2 is 0. X3 is 0. 1, 0, 0. Okay, by taking C as 1, your V1 is 1, 0, 0. Okay, then repeat for the second lambda. Lambda 2 is 2. Lambda 2 is 2. Substitute 2 into lambda, so 3 minus 2. Zero minus 2. 2 minus 2. Okay, so this one we don't have to reduce because this is already in the RDF. Okay, so you just need to identify which is free. Which one is free? X3 is free, so X3 is C. Okay, X3 has no pivot. Then backward substitution. X1 is -6, X2 is 8, X3. So that's mean negative 18C plus 8C, which is negative 10C. Okay, so your V2 is negative 10C, 3C, 3C, and C. So which entry has the largest magnitude? Which entry? This one, right? This has the largest magnitude, -10. So we need to divide all this by -10. So you get a 1, -0.3, -0.1. The largest. When you do the comparison, okay, you just ignore all the negative. Ignore all the negative. You have 3, you have 10, 3, 1. The largest one is this one. Okay. Then you take this here. Okay, but when you do the comparison, just look at the magnitude. Okay, magnitude, that's mean we just look at this 10, 3, 1. Ignore the negative. Okay, then continue to the last lambda 3. Okay, in the next class, we will look at power method, and I want all of you bring your calculator. Okay. You have to get familiar with the calculator, be friends with your calculator. Okay. Otherwise, it won't come you Okay, last lambda. The lambda 3 is 0. Three, 6, 8, 0, 0, 6, 0, 0, 2. Okay, we have to draw reduce because when you sketch for the staircase, non-zero, right? Goes down, turn right. Okay, so we use the 6 to change this into 0. 1/3? Negative 1/3 R2 plus R3. Okay, 3, 6, -8, 0, 0, 6, 0, 0, 0, 0, 0. Okay, so this is your staircase. I1, x1, x2, x3. Which one is 3? X2. X2 is 3. Okay. So backward substitution. X2 plus 8 x3. Okay. So x1 is -8 to C. Okay, B3 is negative 2c, c0. Okay, so by taking c equals to 1, your V3 is negative 2, 1, 0. But we need to divide this by negative 2. Okay, that's negative 0.50. Okay, any questions? Any questions? Okay, so it's already 10:30. We stop our class here, and we look at number 3 in the next class.